Hello guys, and welcome to this video. In this video I'm going to be explaining Raphson's method. So assuming you were given a question like this and you're asked to use Raphson's method to find a root of the following equations, how are you going to go about it? So let's dive into the solution. Okay, so we are going to start with the first one, a x cubed minus x squared minus 1 equal to 0. Now, before I dive into the solution proper, you need to understand what is happening here. Newton-Raphson's method is a method that helps us to numerically approximate the root of a function. Remember that the root of a function is the point where that function crosses the x-axis or crosses the line y equal to 0. Is that okay? So if this is your curve f of x, the root of this particular function, or a root. So we're not going to use the root because the function can have more than one root. So when they usually ask Newton-Raphson's question, they use a root. You will never see them putting the root. Is that okay? So when they ask you to calculate the root using Newton-Raphson's method, they just want you to find a place where the function crosses 0 or crosses the origin, approximates that value. So that is what it meant by the root of a function. So how is Newton-Raphson's method and what is the formula? So you have equal to 0 here, okay? So for this particular one, so Newton-Raphson's method is given by xn plus 1 is equal to xn minus f of xn all over f prime of xn. For the sake of time, I'm not going to do the derivation of this formula here, but I'm going to show you very well how to apply it. Now, this is one component of Newton-Raphson's formula. Okay, Newton-Raphson's formula have about two important components. Okay, so the important components are one, this particular formula, then number two, what we call our error, the error term. Sometimes they might say your error term is plus or minus 10 raised to the power of minus 4 or plus or minus 10 raised to the power of minus 6, etc. Okay, so we have our Newton-Raphson's formula, then we have the error term, okay, and we now have the stop point where you stop or break off points. So the break off point of our Newton-Raphson's formula is when we get to a point such that the xn plus 1 minus the xn, the absolute value of the difference between these 2 points, is less than, or let me say equal to, our epsilon or our error value. Okay, so this is where you're going to stop iterating. Is that okay? So for those of you that are new to this Newton-Raphson's method, I'll take it gently. Number one, you have the formula. This is the formula, and I'll explain how to use it. Number two, you'll be given an error. So typically for these questions, they gave us an error. They said we should use our error to be plus or minus 10 raised to the power of minus 4. So this plus or minus 10 raised to the power of minus 4 means that our error is plus or minus 0.0001. Is that okay? When you evaluate 10 raised to the power of minus 4. So they want us to use it to know when we are going to break away from our iteration or where we are going to stop our iteration. So we'll keep iterating until these values are almost equal to each other. The xn plus 1 and the xn values are almost equal to each other. Is that okay? So having given you this background, we are going to dive into the solution of this particular problem. So given that our error is plus or minus 10 to the power of minus 4, which evaluates to 0.0001, and giving x cubed minus x squared minus 1 equal to 0 to approximate a root. Okay, so we are going to say let f of x be equal to x cubed minus x squared minus 1. So you're going to call f of x whatever is on the left hand side. Make sure that the right hand side of the equation is 0. Then f of x will be called whatever is on the left hand side. Now, Newton-Raphson's formula states that xn plus 1 is given to us as xn minus what? F of xn divided by f prime of xn. So you can see we have f of xn, but we need f prime of xn. Therefore, we need to find f prime of x. Okay, we need to find f prime of x to make the formula complete. So f prime of x is the derivative of this guy, which is a 3x squared minus 2x. Is that okay? So we are going to keep 1, 2, 3. Very handy. So the next thing is to prepare your table. Okay, so to prepare your table, so let's prepare our table like this. So I'm going to give a gap first, and I'll explain why I'm giving that gap. Okay, so the first column is going to be labeled SN. Then the second column is going to be labeled your X subscript N. Then the next column is going to be labeled your F of XN. Then the next one is going to be labeled F prime of XN. Then the last column is going to be labeled as xn plus 1 is equal to xn minus f of xn all over f prime of xn. Typically, this value minus the ratio of these two values will give you your xn plus 1. Is that okay? So we're now going to start with 0. So but the big question is, what is my starting value? So another important component of the Newton-Raphson formula that I missed, okay, is the start value. So the start value in Newton-Raphson formula, sometimes it will be given to you. They will say start with x naught equal to, okay, start value is usually given as x naught, okay, the point that you should start iterating from. Okay, so they might give you in a problem where you should start from your iteration, but sometimes they're not going to give you your x naught. So what do you do in those scenarios when you're not giving your x naught? So if you want to find your x naught, you have to be able to understand that if I want to find a start value, okay, I can use the principle that for an interval a comma b, all right, if f of a is negative and f of b is positive, then there exists a root between a and b. Or if f of b is positive and if f of a is positive and f of b is negative, okay, then there is a root between a and b. So typically, if you compute the function at this point a and you get a sign, and you compute the function at the point b and you get an opposite sign, then it means that there is a root between a and b. I don't know if you're trying to if you're understanding what I'm trying to say. Okay, so if you don't know the start value, you have to start doing trial and error in order to get where you're going to start from in your iteration problem. So given that I've established that, let's try to figure out where we are going to start with for this problem. So f of x is equal to x3 minus x2 minus 1. Okay, so I don't know where to start from, so I'll just start with f of 1. If I start with f of 1, I'll get 1 minus 1 minus 1, which gives me minus 1. Then I'll jump to f of 2. If I go to f of 2, I'll have 2 raised to the power of 3, which is 8, minus 2 raised to the power of 2, which is 4, then minus 1. So 8 minus 4 is 4, and 4 minus 1 is 3. So can you see that f of 1 is negative and f of 2 is what? Positive. So because of f of 1 is negative and f of 2 is positive, or sometimes it might be the other way around, f of 1 might be positive and f of 2 might be negative, but as far as they are different signs, it means that there is a root. This function has a root between the points 1 and 2. So a good point to start your iteration is you can start at the middle point of this particular two values, 1 and 2. So I'm going to start my x naught as what? 1.5. Is that okay? So 1.5 will be my x naught. Then I'm now going to evaluate xn, then f prime of xn. Then I'll now finally evaluate xn plus 1 as xn minus f of xn all over what? F prime of xn. So this is just what you're going to be repeating till this condition is satisfied. That's your break-off point. Is that okay? So now that we've established our start value, so let's jump to the computation of the f of xn and the f prime of xn. So take note, my x naught is what? 1.5. So let's x naught be 1.5, the starting value. So let's go to a calculator, and we're now going to start calculating proper. So we are going to calculate our f of x. Our f of x is something cube minus something square minus 1. So something like this: something cube minus something squared minus 1. Okay, so this time around I'm dealing with what? 1.5 as my starting point. 1.5. So f of 1.5 gives me 0.125. So 0.125. So I'll put it here. So what is f prime of this same xn? So f prime of 1 to 5. Remember, f prime is your derivative, so you should keep your derivative handy alongside your normal function. So my f prime of x is 3x minus 2. So in the calculator, I could just easily do something like this. 3x squared, okay, minus 2 times this value. So I'll just remove the square from this one and remove the 1 like this. So this value will help me to compute 3x squared minus 2x. Okay, 3x squared minus 2x. And take note, the x in question is the 1.5, our start value. Is that okay? So if I compute it, I'm going to get 3.75. So now that I've gotten this point, that's my f of xn and f prime of xn, I can now substitute them into this formula to get the new xn plus 1. So the new xn plus 1 will be the old xn, something like this, 1.5 minus the ratio between f of xn and f prime of xn. So f of xn is 0.125 like we got, and f prime of xn is 3.75. Is that okay? So this gives me a 1.466667. I'll work with 6 decimal places, and I'll advise you to do the same in all your calculations. Work with 6 decimal places before you finally approximate. So 1.466667. Is that okay? So now that we've gotten this value, we are now going to transfer this value to this point as the new start value now. So 1.466667. So any value you get here will be transferred to this point as your new value. Then you now repeat the same process. Is that okay? So this is x naught, this is x1. Okay, so x1 is the value that we computed from x naught, so we'll transfer it here. We'll now repeat the same process. Now as you're repeating the same process, be comparing this and this. If you are getting the correct answer, you will see at a point that this answer and this one, they will not be so different from each other. So let's keep solving, then you see what I'm trying to say. So we are going to use this value as the new starting point. So we are going to evaluate f of this particular value now. So f of this particular value, as usual, you have something cube minus something squared minus 1. So remember, our f of x is something cube minus something square minus 1, and my f prime of x is what? 3 something square minus 2 something. So these are the references that I'll be using to compute the values. So we are dealing with the something at this point as 1.466667. Okay, so you just fill it there, 1.466667. So when you evaluate it, you get 0.00385 to 6 decimal places. 0.00000, sorry, 3853 to 6 decimal places. So we'll compute f prime of this point. So computing f prime of this point is just changing this one to square, then bringing the 3. Okay, like you're differentiating, here is 2 times, and this one is not there, then remove the 1. So 3 something square minus 2 something, just like we established here. 3 something square minus 2 something. So that evaluates to 3.520000. So we have 3.5200 to 6 decimal places. Okay, so how do I now compute this value over here? I'll compute it by saying this point minus the ratio between this and this. So something like this new point, 1.466667, minus the ratio between the f of xn and the f prime of xn, which we got as 0.003853. okay, minus divided by 3.52. oh, that's a 3.52000 and 2, like this. So we're getting 1.465572. so 1.465572, 1.465572. So we are now going to transfer this point as the new starting value. So 1.465572. So do you see that this point and this point are gradually begin to look like each other? So you can see that they are looking like each other. So we'll now compute it again. Is that okay? So we'll compute it by substituting this point into the function, substituting it into the prime of the function, and we'll now repeat this step here. So let's do that all together. So in the original function, we have something cube minus something square minus 1, giving me something cube minus something squared minus 1, and that something in this case is 1.465572. So we have 1.465572. That okay? So this gives me a 2.69 exponential minus 6. So this means exponential minus 6 will have 5 zeros before the number. 0.12345. Then you now have 2 7 approximately. Okay, 269 is 27 approximately. Is that okay? So you're going to evaluate the prime. Okay, the prime is going to be 3 times something squared minus 2 times something. Okay, and that something is still the point in question, 1.465572. okay, then 1.465572. So that gives me 3.51 0.2560 approximately. So I have this value as my xn, then this is my f of xn and f prime of xn, and I'll now use this formula by saying this minus this divided by this. Is that okay? So this minus this divided by this, so it's going to be like this: 1.465572 minus the ratio 0.002000027 divided by 3.512560. So this gives me 1.465571. 1.465571. Okay, 1.465571. So let me just put it like this. Now if you take this value over to this place, you get 1.4655712. Okay, now you see that this value is almost exactly to this one, so there's no need of continuing. So we're just gonna break off here, and we can also convince our lecturers, since we see that this one and this one are almost the same, by saying our okay, this is x, this is iteration 2 and this is iteration 3, so you can say your x3 minus x2. Okay, that's this value here, the absolute value of these two guys, which is going to be 1.4655712 minus 1.4655572. Okay, the absolute value of these two is equal to what? So let's calculate it. So we have 1.4655712 minus 1.4655572. You get you get minus 8 exponential, okay, 7. So we have something like this: 0.1234568. So this is negative like this, and definitely this value is less than our epsilon. Now epsilon is 10 raised to the power of minus 4. Is that okay? 10 raised to the power of minus 4. So you can see that at this point you can stop here. So we can stop. So the implication is that a root of f of x equal to x cubed minus x squared minus 1 is approximately x3, which is approximately 1.46555, okay, 7 2. So if we want to leave it to an accuracy of 4 decimal places, just like any number up here suggests, an accuracy of 4 decimal places will be 1.46556 approximately. So this is going to be a root of this particular function. Is that okay? So this is all about Newton-Raphson's method. So just to tell you how fun Newton-Raphson's iteration method is, I decided to write a Python program that could actually compute Newton-Raphson method. So you don't have to understand the complexity of the program now. Definitely, I believe you're learning how to code in one way or the other. So I have written the Python function, and the Python function takes in some parameters, and this Newton-Raphson function is limited to only polynomials. Unfortunately, this function that I wrote cannot handle special functions like exponential or trigonometric functions, it can only handle polynomials. So the first parameter here is the degree of the polynomial. So is the polynomial the highest degree 3 or 4 or 5 or 6? So the second parameter here is the error, that's the epsilon value or the accuracy. Then this value here is the start value, okay, the start value. Then any other value that is following at this point will be the coefficient of our polynomial. Is that okay? So the polynomial that we are given, I just wanted to verify that we'll get the same answer here with my Python calculator. You have f of x is given to us as x cube, okay, minus x square minus 1. So if I complete this polynomial, I have x cube, okay, then minus x square, then plus 0x, then minus 1. So these are the coefficients of this polynomial. You see, this polynomial is a polynomial of degree 3. Okay, so my start value for my iteration x naught is 1.5, like we established above, and our epsilon given from the question is 0.0001. okay, that's plus or minus 10 raised to the power of negative 4. So having all this information, I'm just going to plug it into my Newton-Raphson calculator. So the polynomial is of degree 3. The epsilon value is 0.0001. The start value is 1.5. Then the first coefficient is 1. Okay, that's the coefficient of x cubed. Then this minus 1 is the coefficient of minus what? So of x squared, sorry. So the coefficient of x is 0, then the constant term is minus 1, like this. So by the time I try to print the answer of this function, you will discover that this is what we got. Okay, so this is what we got. As you can see, it is almost the same with what I calculated, 1.465571. okay, approximately 712. So that was where we stopped at when we were calculating on our table. So 1.4655712. So this Newton-Raphson's calculator is just combining algorithms from the theory of the Newton-Raphson's method and a little of your knowledge of coding to implement the method. So I just implement it so that you see that it is fun, and the method is actually a legit method of computing a root of a particular function. So when we are given polynomials, you can trust my Newton-Raphson calculator to deliver the exact answer. So if you want to learn how to code this particular stuff, you could just leave a comment and I will provide you with a GitHub repository to where I have stored the code for this Newton-Raphson calculator. So that's about this question. So we're going to go to the next question now, and the next question is going to be this one. All right, so I'm going to solve this one, then I'll leave you to try this one by yourself. I'll leave you to try this one by yourself from the knowledge you got from this and this. Is that okay? So let's jump to the solution of this second one so that we can understand more about the Newton-Raphson's method. Okay, so in the second place, solution 2, we are given tan z equal to z, tan z equal to z, and the same conditions still apply. Our epsilon is plus or minus 10 to the power of minus 4. That's our breaking value. So we want to find a root. So how do we go about this? So this is how we go about this. First of all, you're going to say tan z minus z is equal to 0. So having expressed it like this, you're going to say let f of z be tan z minus z. Now take note, you have tan z minus z, so every calculation will be done in radians. So you're going to program your scientific calculator to compute these values in radians. Okay, you're not going to use degrees. Be very conscious of this. So let's see what we need to get to solve for a root of this particular function. So first of all, we need to try to figure out what z naught is going to be. So what is z naught? The starting point, starting value. Now, this particular function is a very, very complicated function, and let me show you why it's a very, very complicated function. Okay, so if they give you this kind of question in an exam scenario, I expect the lecturers or whoever sets the question to provide a starting value. Okay, a starting value that will help you not to calculate infinite iterations, because there are some times that if you choose the wrong starting value, you're going to iterate infinitely and you won't even get the right answer. So you have to be very, very careful in your choice of your starting value. Okay, so let me show you the function of the graph of this function, so that you understand how it is. So I'm just going to plot tan taking x as z minus x. So this is in radians, and I press enter. So now this is how complicated this function looks. Okay, so this is how complicated it looks. So let's analyze the function together. Now the function has asymptotes. All these vertical lines are called the asymptotes of this particular function. Now this curved line, okay, is having the property of our normal tan function, and you can see that this function will have infinitely many roots. Any place where this curved line crosses the x-axis, that is a root. So one possible root is at point 0. Okay, another possible root is in between 4 and 5. Another possible root is in between 7 and 8. As you can see, the curve crosses between 7 and 8. Another possible root is between 9 and 10. So another possible root is between -5 and -4. Anywhere this curve crosses the x-axis is a possible root. So for now, I'm going to avoid calculations around this point 0, because everybody knows that 0 is obviously a root of this particular function. Even without calculating, you can calculate it analytically. Tan 0 minus 0 is going to give you 0. Okay, so 0 is a possible root. Tan 0 is 0 even in radians, then minus the point 0. 0 minus 0 is 0. So 0 is the possible root. So another root that I'm going to be interested in is the root that lies between 4 and 5. The root that lies between 4 and 5. I don't know the exact value of this root for now, but we are going to compute it together. So we are going to make our starting value to be in such a way that it exists between 4 and 5. Okay, so if you're given this question in exam and you're not giving a start value, use a value between 4 and 5. Okay, so I'm going to choose z naught to be between 4 and 5. So let's say z naught is 4.5. That's our start value. So the start value is very important in any Newton Raphson iteration. Okay, so the start value is very, very critically important. Now we have established our start value, so the next thing we need to do is to create the table. So creating the table will be like before. So the first column will be our serial number to keep track of the iteration points that we are currently. So we now have our Zn. Okay, then we'll have our f of Zn, and we'll have our f prime of Zn. Then finally we're now going to have our Zn plus 1. Zn plus 1 is, by Newton-Raphson formula, Zn minus the difference between the ratio of this particular terms. So Zn minus the ratio between your f of z and f prime of z. Is that okay? So we are starting with 4.5. So let's compute f of Zn and f prime of Zn. Now before we go any further, we also need to try to compute our f of Zn and f prime of Zn. Now my f of z is already given to me as tan z minus z. if you want to compute f prime of z, you need to differentiate. Differentiating tan z, you get sec square z, okay? And differentiating z with respect to z, you get 1. Now, I want you to know that on your calculator, you might not have the luxury of seeing, you might not have the luxury of seeing sec on your calculator. So you have to remember that your sec is still the same thing as 1 all over cos. Okay, so this is 1 over cos square z minus 1. If you're implementing this in a calculator, it's still the same thing as you saying your f of z is, by law of indices, cos z all raised to the power of minus 2. Okay, so your cos z to the minus 2 minus 1. So this is how I'm going to calculate it on my calculator. So my f of z will be tan z minus z, and my f prime of z will be cos z to the minus 2 minus 1. This is not cos inverse, please. This is cos z all raised to the power of minus 2. Is that okay? So let's begin the computation right away. So f of z, starting with 4.5. So we have tan 4.5 minus 4.5. That's tan z minus z. Is that okay? So this evaluates to 0.137332. So 6 decimal places, 0.137332. Is that okay? So we are going to evaluate f prime of z, which is cos z. So we have our cos z, which is cos 4.5, the starting value, then raised to the power of minus 2. So it is not the 4.5 that is raised to the power of minus 2, but the entire cos itself. Okay, minus 1. So cos 4.5 to the minus 2 minus 1. And this cos 4.5 to the minus 2 is still the same thing as sec square. Okay, 4.5. So this gives me a 21.504849. So a 21.504849 to 6 decimal place. So to compute my Zn plus 1, I'm going to say Zn plus 1 is this value minus this over this. Is that okay? So we have 4.5 minus, the first is 0.137332 divided by 21.504849. 504849. So this gives me a 4.493614. 4.493614, like this. So as usual, we are going to transfer this value to be our new start value, 4.493614. Then we'll now repeat the process. Is that okay? So we are at we've crossed from the 0 iteration to the 1th iteration. So I'm going to compute f of zn, where zn is this particular value. So as usual, computing f of something, you have tan something minus that thing. So in this case, we have tan 4.49 4.493614 minus the same 4.493614, because our f of z is tan z minus z. So 4.493614. So this gives me 0.004134. So 0.004134, approximately 0.004134 to 6 decimal place. So let's compute f prime of zn. This time around is cos. Okay, so cos z always to the power of minus 2, then minus 1. So you have cos z, in this case is the point in question, that's the 4.493614. 4.493614 all raised to the power of minus 2 and minus 1. Okay, so this gives me a 20.229736. 4.229736 to 6 decimal place. So as usual, we'll compute the Zn plus 1 by by subtracting this from the quotient between this and this. Okay, so that's how we're going to set it up, like this: 4.493614 minus the ratio, that's the f of z, is 0.004314, divided by the 20.229736, like this, and this gives me a 4.4934 and 0.1 approximately, okay, to 6 decimal places. So we're going to continue our iteration by setting this value to be here as the new value, 4.4934. We have 0.1. Okay, then we're now going to compute our f of z. Our f of z is what? Very good, tan z minus z. So with this new value we just computed, which is our new start value, we'll compute the f of z, which is tan z minus z. So tan z, which is the 4.493401, tan z minus z minus 4.493401. Okay, so this gives me minus 0.000 minus 0.000171 approximately, minus 0.000171. Okay, so we are going to calculate f prime of zn. Okay, f prime of zn. So f prime of zn is our cos z to the minus 2, then minus 1. So we have cos that point 4.49. We have 3401 all to the minus 2 and minus 1, which gives me a 20.1891 and 18 approximately. Okay, so 1891 then 18 approximately. So we are now going to compute this, that's this value minus this divided by this. So we have the 4.493401, then minus the ratio between, you have minus 0.000171 divided by 20.19, sorry, 189,118. So I have 4.493409. Okay, so you have 4.493409. So you can see that at this point now the value is struggling to change. So we have 4.493409. So if you count the first 4 decimal values, which is a 10 to the power of minus 4, if you count the first 4 decimal values and you see that they correspond to each other from the second iteration, from the 2 iteration to the 3rd iteration, that's iteration on index 3, you can now stop, because if you evaluate your x3 minus x2, the absolute value, you discover that is going to be equal to 4.493409 minus 4.493409. 3401. So let's compute this and see what we get. So 4.49340 minus 4.493401. We're getting 8 exponential 6. That means we're getting a 0.0000008. Okay, and this is clearly less than our epsilon value, which is a 10 to the power of minus 4. Okay, so at this point we can now stop. Is that okay? So you can stop your calculations, okay, just when you notice that this value, this first 4 is equal to this first 4, depending on the number here in your epsilon. Your epsilon is 10 to the minus 4. So count whatever number of decimal places is represented here. You have 1, 2, 3, 4. If one iteration have the same number of decimal places as the next iteration based on the value of your epsilon given, then that's where you stop. So you don't need to continue anything here. So you can now say, therefore, a root of f of z equal to what? Tan z, okay, minus z is approximately 4.4934. Okay, now we are working with 4 decimal places. Is that okay? 4.4934 is an approximate decimal point. So let me try to show you on the graph again that this value is almost correct. So tan x minus x. So if I go to that value and I press on it, you see 4.49340963. So this is approximately almost what we calculated with the Newton-Raphson's formula. So you see that this formula is legit. So I hope you understood how to, implement your Newton-Raphson's formula. So at this point, I'm going to be wrapping it up. And for the third exercise, for the third problem, you're going to try to do it by yourself. So what's the third problem again? The third problem is given to us as this one over here. So your task will be to find a good point to start. So you're going to interpolate, plug in values, and you see when a value change sign from the next value that you implement. Let's say I plug in 1, I observe the value. I plug in 2, I observe the value. So I'll keep plugging till one value changes sign from the other value. So if 2 value, I observe that by plugging in those values, and I discover that the value of the function changed sign from positive to negative or negative to positive, then I'll now take my start value as any number in between those 2 points, just like I did in the first case. Is that okay? So that's where we'll now start iterating from, and you're going to iterate, follow the process judiciously to you get to a point where your x values are struggling to change. So with this, we've come to the end of Newton-Raphson. I hope I demonstrated it well enough to a level that you can understand and implement even in exam scenario. So try to do this last one by yourself, and I believe you'll be all right. So yeah, that's about it. Good luck.